One, thanks for giving this opportunity to express and discuss quite a lot of topics online with so many excellent researchers. My name is Peng Jin, and I'm from Southeast University. During the next few minutes, I'm going to introduce our team's work on the carbonation process of C2S, specifically the effect of carbonic anhydrase bacteria on the carbonation of C2S. As known to us all, too much carbon dioxide emitted into the air might lead to many serious consequences, such as global warming, adverse weather, and so on. Although many methods have been taken to reduce the carbon emission, it still increases apace year by year. Take China as an example. We have established the carbon emissions trading market and are going to spend $275 billion on the treatment of the atmospheric environment during the next 5 years. As one of the main byproducts of steelmaking process, it's a huge waste that the utilization ratio of steel slag is still no more than 30%. Steel slag has some similarities with Portland cement, especially for the basic oxygen furnace slag. Relatively higher content of C2S induce steel slag higher carbonation activity and make it possible for steel slag products strengthened by means of carbonation. Next. One type of carbonic anhydrase bacteria named Bacillus mucilaginous, which could accelerate the hydration rate of CO2 up to 10 to 11 times theoretically, was introduced to the carbonation process. As shown in this slide, the catalysis of CO2 hydration is initiated by the nucleophilic attack on the carbon atom of CO2 by zinc bond OH, that is hydroxide radical, to produce bicarbonate, which is then displaced from zinc by a water molecule. From another point of view, the negatively charged bacteria bond with the calcium ions in the solution, which could provide independent nucleation site to promote the formation of calcium carbonate. More carbonation products here are calcium carbonate, and through SEM images here, it is obvious to find that after carbonation, the microstructure is denser than before, and evident calcite particles can be detected in the capillary pores. These comparisons could directly reflect the effect of biocarbonation here, which has the densest microstructure after only 2 hours of carbonation. Steel slag consists of so many kinds of mineral phases which vary a lot with different steelmaking processes. However, most kinds of steel slag have a certain amount of C2S, including 2 crystal forms, beta C2S and gamma C2S. Beta C2S is one of the most significant minerals in Portland cement because of its relatively low hydration reactivity compared with C3S, which could compensate the long-term strength. Almost pure beta C2S was synthesized to conduct this carbonation experiment, and results show that the compressive strength was improved by 1,355.1% within 1 hour. With the addition of carbonic anhydrase bacteria, from those 2 micro-CT images, the carbonation depth was increased from 30.2% to 34.4%. From the aspects of carbonation products, it's obvious that there is more gel content in the center part of the specimens as well as unreacted beta-C2S particles, which may indicate that the hydration of carbonation process of beta-C2S, that is, beta-C2S hydrates first as the equation here, forming CSH gel and portlandite. Then portlandite is carbonated to form calcium carbonate, while presumably CSH gel can also be carbonated because of the less content at the edge of the specimens. The less content of CSH gel at the edge of the specimens. Here is a conceptual model about the distribution of carbonated products, which could help to understand the carbonation process of beta-C2S. More detailed research can be found in this article. On this slide, it is obvious to find that calcium carbonate in biocarbonated beta-C2S is the overlapped nanoscale calcite calcium carbonate, while that in directly carbonated beta-C2S is typical microscale rhombohedral calcite, which might be affected by the extracellular polymer or other organic matters released during the metabolism process of bacteria. Apart from physical filling effect and chemical binding effect, nanoscale calcium carbonate can also act as the nucleation sites, promoting the formation of CSH gel, that is, promoting the hydration of beta-C2S, thereby promoting the carbonation process. As expected, pore structure has changed a lot during carbonation process, which is in line with the improvement of mechanical and durable properties. Okay. Gamma C2S is another significant composition in steel slag, whose properties are different from that of beta C2S. It has relatively lower hydration reactivity, but higher carbonation reactivity. From both those 2D and 3D micro-CT images, the addition of carbonic anhydrase bacteria decreased the carbonation depths of the carbonated specimens. However, this is not equal to side effects of bacteria because, in my opinion, carbonation degree and carbonation depths should be divided as two conceptions and two factors. They are different from each other. Those two factors affect the final performance of carbonated C2S together. Some more details can be found in this article, and time is limited here, so I cannot explain too much. As shown in this schematic diagram anyway, cyanobacteria accelerate the hydration of CO2 and promote the carbonation process, contributing to higher carbonation degree at the edge of the specimens. However, the rapidly formed carbonate film and the accelerated dissolution of CO2 inhibited CO2 diffusion, leading to smaller carbonation depths. When it comes to carbonation products of gamma C2S, it is quite different from those of beta C2S. There is no nanoscale calcium carbonate, and only a trace of silic gel can be detected because of a band shift from lower wave number to higher one. Vaterite can also be detected by XRD. That is, cyanobacteria has little effect on carbonation products of gamma C2S. In conclusion, carbonic anhydrase bacteria could induce the precipitation of nanoscale calcite through EPS or other organic materials released during metabolism process during the carbonation process of beta-citrase, while it has little effect on the carbonation products of gamma-citrase. Simultaneously, it could accelerate the hydration of CO2, hence increase the carbonation rate and efficiency. This technology may have profound application in the future. The concept of sponge city has been accepted in many cities and countries. Hence, biocarbonation technology could be applied to the precipitation of permeable paving materials, which has a similar performance with porous concrete. I hope our team's work could be helpful to the improvement of the production process of such kind of materials, as well as give inspirations to other relevant researches. Thanks for your kindly listening. Questions and discussions are welcome.